First, and at the request of my daughter, I am taking part in something called December, which is why I'm wearing a tie. She's wearing a dress every day of the month and is encouraging other people to participate. Women, you can wear dresses, men, you can wear ties. And take part in December if you want to wear those things every day as a way to raise awareness about human trafficking. You can even think of it as modern day slavery. People are really being sold, sex trafficking and violence against the poor. And not just in foreign countries, but also in America that happens. We're not really aware of it. So anytime you see somebody wearing a dress or a tie this month, you can think about that and contribute money if you want. You also in January, my daughter's showing a video called Nefarious, which is about human trafficking that you can watch then. But again, I'm going to be wearing a tie every day. Today it's a Snoopy tie. So you can zoom in on this if you like here. So you can see the Snoopy there. I actually don't have any ties. And in fact, this is the only creative tie that I have. And it was just given to me a week and a half ago, in fact. So I'm also going to give you an opportunity to send me ties. We only have 5 days of class left after today, so I won't be able to wear everybody's tie. I suppose I could wear more than one tie at a time, maybe. I don't know, that'd be really strange. But if you'd like to donate a creative tie to me, make sure your name is on, and make sure you don't mind it being on YouTube. And maybe I'll also say your name to acknowledge who did it. I might not be able to wear everybody's tie that everybody gives to me. I'll probably try to pick the ones that I like the best. So we'll see. But again, just think of it as a way of raising awareness about a serious issue when you see people wearing ties or dresses. All right, today I want to spend time doing two main things. That's reviewing the idea of a change of variables to integrate over a parallelogram, and also get a little bit into triple integrals in alternative coordinate systems. In the last class, I went too slow on the change of variables, the general change of variables. I only had 5 minutes to talk about triple integrals. So I'm going to try to go faster with you guys about the general change of variables. There's a lot of Mathematica code and a lot of explanation. I'm not going to explain the Mathematica code. I'm probably not going to explain my explanations that much. I'm just going to show you things and verbalize it and go pretty fast. If you then download the notebook off of Moodle and take the time to read what I wrote and to run the code and experiment with the code yourself, I think you'll get more out of it because I'm going to go pretty fast. So here again was our problem from the last class period a week ago. We've got this lamina, which again is just a word for a thin sheet of metal or whatever that's shaped like a parallelogram. The parallelogram had vertices at 0, 0, 5, 1, 7, 7, and 2, 6. About like that. And we had this density function that I've been calling it rho, but it's actually unfortunate to call it rho when we use spherical coordinates because rho represents the distance to the origin for spherical coordinates. Anyway, when we get to the problem about triple integrals, I'll probably call it f instead of rho. Here's our density function in grams per square centimeter. We can enter that. Again, we can look at the contour plot. And I think it is definitely a good idea to try to guess the value of the integral just from the contour plot, as I have been emphasizing. Let me try to make it a little bit more precise about what I've been doing here. You can say the average density. Well, I've been thinking of it as a quantity that you can multiply the area by. The area of the domain D to give you the value of the integral. That's the way I've been trying to emphasize that you can think about the average density, and that should make sense. If it was a uniform density, a constant density, say 50 grams per square centimeter, you'd take that constant density and you'd multiply it times the area in square centimeters to get the total mass in grams. Both sides here represent the total mass. Now I was just approximating the average density to try to help me estimate the integral. The area here you can find exactly, and you can find it exactly using that problem that you did for a graded problem back a couple months ago, where you calculate the determinant of a matrix formed by making the rows of the matrix the position vectors that I'm drawing right here, right now. Those two vectors. This vector being the vector whose components are 5 and 1, and this vector being the vector whose components are 2 and 6. Make a matrix with those vectors as the rows, and calculate the determinant of that, and take its absolute value, and you're going to get the area of the parallelogram. In this case, we get 28 for the area of the parallelogram. So again, I was trying to estimate the average density. I looked at this picture and said, well, you know, it's sort of mostly in dark instead of light. It's sort of more of the region is in lower values of the density than higher values. So I guessed more toward the low side for the average value. You can see these numbers are in the 30s, 40s, 50s, 60s. These numbers get pretty high up here, 200s, over 300 even. But I guessed something in the 50s, 60s, 70s, and in fact, in the last class period, I guessed 64.5 eventually, and that's pretty close to the right answer. This code right here calculates the correct answer exactly. 1808.3 repeating. It is over 3 here. And that's pretty close to 1806. But in reality, what's really going on here is this equation can be used to define what average density is. Maybe you divide both sides by the area. You could say the average density, by definition, is the total mass, which is represented by the integral, and divide by the area. By the way, this determinant calculation here is very similar to the determinant calculation for the Jacobian. Okay? It's a pretty similar idea. In fact, I'll show you more explicitly in a few minutes why. What did we do that made this the integral a little simpler? Instead of adding together 3 integrals that were fairly complicated, we just did one kind of complicated integral. It was a little easier because the limits of integration ended up being constant. It's way down here. That's why I'm saying you're going to have to look at this code and these explanations after class sometime. What we did was we ultimately had a change of variables. Let's try to quickly review what that was. This line had equation y equals x over 5. This one was y equals 3x. This one was y equals 3x minus 14. This one was y equals, I forget, it was 1/5 x something. 1/5 x minus 2 plus 6 works. That simplifies to 1/5 x minus 2/5 plus 30/5 is plus 28/5. We rewrote those equations. For example, this equation was written after multiplying both sides by 5 and subtracting y from both sides as 5x minus, x minus 5y equals 0. That's an equivalent form of that equation. It gives you the exact same line. Ultimately, this led us to our transformation, our g function. Where is it here? Way up here, I think. Here it is. Is that it? No, that's actually not it. Here's the way I described it initially. I described D in this way. That's the parallelogram described in terms of x and y in probably the simplest way possible. 3x minus y is between 0 and 14, and x minus 5y, that quantity, is between 0 and negative 28 when it's up here. If you rewrite this by multiplying both sides by 5, subtracting 5y, and then also putting the 28 on the other side, you get negative 28 on the other side, which is why we have negative 28 there. That description of the domain made me say, okay, maybe I should let u equal this and let v equal that. That's the new variables, u and v, u is 3x minus y, v is x minus 5y. And we solved algebraically for x and y in terms of u and v. That's what this code does. Got these equations, and essentially these equations define that g function in the book. They define the mapping, and that's what I'm entering down here. And then, once we've got that mapping, we can find its Jacobian matrix, we can find the Jacobian determinant. And that ended up being 1/14. And that's why way down here, when we do the integral, that's why we have the extra factor of 1/14 here. We plug in how x and y depend on u and v into rho. We get this expression. But that's not the expression to integrate by itself. You also have to multiply that expression by the absolute value of the Jacobian determinant, which is 1/14. And it gives you the same answer. This is the exact same answer as before for the total mass. Okay? I do want to show you that the book gives you a method for this kind of problem that is a little easier, maybe not easier, but it's quicker. Instead of defining u and v first in terms of x and y, and then solving for x and y in terms of u and v, there's a quick way to write down how x and y depend on u and v right away without doing much work, actually. What you do is you look at these vectors, and you make those the columns of a matrix of equations, so to speak. Make 5 and 1 there, say, the coefficients of u in both equations, and make the components of the other vector, 2 and 6, the coefficients of v in both equations. And that is a quicker way to define a transformation, a mapping, from the UV plane to the XY plane whose image will be that parallelogram. When you take the domain of this mapping to be a very simple square, this square right here on the UV plane, a square of area 1. This mapping works. Its Jacobian determinant. Again, what's the capital G function? The capital G function in this example is a point whose coordinates are given by these equations. 5u plus 2v and u plus 6v. That's how these equations give rise to a mapping, a function. The Jacobian determinant of G, which is written like this sometimes, also written in this really odd way, as sort of a strange partial derivative, can be found by taking essentially the determinant of the matrix you would get by putting those coefficients 5, 2, 1, and 6 into a matrix, because those numbers are going to be the partial derivatives. In terms of partial derivatives, it's dx du times dy dv minus dx dv times dy du. And those are going to be constants in this example. dx du is 5, dy du is 6, excuse me, dy dv. 5 times 6 minus dx dv is 2, and dy du is 1. And you can see we are essentially taking a determinant of a matrix. 5 times 6 minus 2 times 1. To get 30 minus 2 is 28. That seems familiar. This square has area 1. This new mapping, which is different than the other mapping I showed you, maps this square of area 1 onto that parallelogram that's got area 28. That's why you get the extra factor of 28 here. I guess there is the downside in this case that you still have to solve a system of equations, so this is not necessarily simpler. You still do have to solve those equations for u and v. No, excuse me, I'm wrong. You can plug those right away into rho. So it is a simpler approach. So I could take rho and plug in those equations that I circled for the x and y coordinates of rho, for the inputs of rho. 5u plus 5u plus 2v and u plus 6v to give me the expression that I would integrate after I also multiply it times the absolute value of the Jacobian determinant. There it is. I guess that's not as simplified as I was hoping. Expand will work better there. There we go. So, if I now integrate that function times 28, as u and v both go from 0 to 1 now, so these are also simpler limits of integration, integrate this thing times 28, because that again is the value of the Jacobian determinant, both in value and absolute value. du dv, it doesn't matter which order you do it here because the limits of integration are both 0 and 1. This should be the same answer. Yep. Okay? So there's more than one way to do this, okay? The method I showed you a week ago is fine, but this method that's described in the book is a little quicker. I think maybe my method was maybe a little bit more intuitive because we were describing the region as being between two quantities that depended on both x and y. And it led to a little bit more natural substitution. But the book's method here of taking these vectors that span this parallelogram and making them the coefficients of u and v, that is a little quicker method. You can use either method to integrate over the parallelogram. What's going on here in a visual way? I showed you some kind of neat graphics here. Look at this one here. I want to put curvy braces around u and v here. What's really going on? Actually, this is the first example. This is the example that I did from a week ago. I can tell by the fact that, well, okay, maybe I need to re-enter G. Actually, let me go ahead. I guess that G is entered. Okay, this is the original example from a week ago. So, in the original example from a week ago, U went from 0 to 14. V went from negative 28 up to 0. This is a UV plane that I'm imagining a rectangle being in. And ultimately, you're integrating over that rectangle with respect to U and V. And by the way, I had a typo, so to speak, in the last class. That when I put it on YouTube, I made a little note that it was a mistake. In terms of the new coordinate system, the dA is equal to the absolute value of the Jacobian determinant. Again, has this odd notation, times du dv. I accidentally wrote dx dy. Okay? When I say times, I mean times in quotes. It's just an imagination. You're imagining that you're multiplying these things. It's not literally what's going on. But that's what dA becomes in terms of new variables u and v. And again, what's going on here with this picture, I showed you a picture like this in polar coordinates before. I will raise the screen again in case you haven't quite finished writing that down. Now we're doing this new coordinate system. What happens here as this animation parameter goes from 0 to 1? We see the effect of the mapping. We see the original rectangle in the UV plane get mapped to the parallelogram in the XY plane. And look, isn't that cool? I also made my axes labels change depending on whether lambda was 0 or 1. So when lambda is 0, you see the UV plane. When lambda is 1, you see the XY plane. In between, what plane is it? Just don't label the axes, okay? These in-between planes are just for fun, again, right? I'm doing what you might call a linear interpolation between these two sets. You really don't care about the in-between stuff, except as a nice visual way of imagining what's going on. And it is a nice visual way to imagine. It even includes sort of like a little flip of the region. You see that there? It's almost like it flips, it rotates or something in the third dimension. That's actually reflected by the fact that the Jacobian determinant was negative. It was negative 1/14 in the example that I did. So it's not just its absolute value indicating that all the areas are getting shrunk by 14, a factor of 1/14, but the fact that it was negative 1/14 is a way of getting that twisting effect that you see there in the math. There is one more way to think about this stuff that is sometimes handy. You can also think of this stuff purely in terms of the XY plane, the original plane, except you also add into this plane, this picture, a new coordinate system based on slanted axes. Here's what I mean. Take a look at that picture there. So this is the original XY plane. I probably should have labeled the regular axes here, X and Y. And the shaded thing here, it's hard to tell it's shaded, isn't it? Shaded thing right there, that's the original parallelogram. In the XY coordinate system, this point up there is at point 77. What is that point in the UV coordinate system? Actually, I think I've constructed this in such a way that these slanted axes that you see, the red axis here is the U axis and the blue axis is the V axis. Since V went from negative 28 up to 0, I guess the positive V axis is actually down over here. So the positive U axis goes that way, the positive V axis goes this way. And in terms of these slanted axes, in terms of U and V, the coordinates at that point are U equals 14 and V equals negative 28. That doesn't mean the distance between that point and the origin can be found by taking the square root of 14 squared plus 28 squared. It means I created a new coordinate system where distances are measured differently as well. In the original coordinate system, that distance right there is about 1 unit. But in the new coordinate system, this distance right there is actually 3.5 units. 3.5, 7, 10.5, 14 bring you right there. It's kind of like transitioning between, say, centimeters and inches. It's like you're using a different kind of measurement system, if you want to think of it that way. So that is another way of thinking about what's going on, though it's not the main way we focused on. All this stuff, again, works in polar coordinates. Here's an example of polar coordinates. So now we have a disk as our lamina. We again have a density function. The density function this time, you can see up there, is x squared plus y squared plus 50. It's got lower values down here that are in the 20s and 30s. Grams per square centimeters, and higher values up here in the 50s, 60s, 70s. As far as the shading goes, most of this is light. There's a very small area down here that's darker. So I should expect the average density to be more toward the higher region, perhaps 50, 60, something like that. Actually, I guessed in the last class in the 50s, and I finally whittled it down to being pretty close to 52.3. The average density. Why? Because when I multiply that density times the area of the disk, which is 9 pi, the radius is 3, so you have pi times 3 squared for the area, 9 pi. You multiply that times the guess for the average density, you get this, which is pretty close to the value of the integral. The value of the integral is 1477.33 approximately. Okay, so again, that gives meaning to what you should expect for the answer. How about doing that integral by hand? What if you had to do that in the final exam? You should hope that I don't ask you to do this double integral on the final exam. As is. Okay? Converting it to polar coordinates is easier and definitely more doable, but as is, it's not so pleasant. The function rho is not too bad. Integrating that with respect to y, just in terms of an antiderivative, is pretty easy. 50y plus x squared times y plus y to the 4th over 4. However, when you plug in the limits of integration, you get that thing. So doing the outer integral would definitely be too hard for a test to do by hand. You have to do a trig substitution. X is 3 sine theta. And again, we did a problem like that the first few weeks of class, where we were calculating an arc length, the distance traveled, I believe. And that was that integral that took up the entire board pretty much. You don't want to have to do that one by hand. But if you convert to polar coordinates and use the appropriate absolute value of the Jacobian determinant, which is what here in this case? It is r. In other words, use dA equals r dr d theta, right? Which you already knew. The integral, while not super easy, is doable. Here it is down here. You have to get the function in terms of rho r and theta. Here it is. When you integrate that, you've got to multiply it times r. Don't forget to do that. There will be another double integral on the final exam where you've got to use polar coordinates. People did forget to do this sometimes. Some of you forgot to add the extra times r in there on exam 3. That was still a common mistake. Doing the inner integral here is not too bad. Excuse me. You're doing it with respect to r, which is down here. Excuse me. That's the inner integral. It gives you this, and this is what you now have to integrate from 0 to 2 pi. And though that looks difficult, it's not too bad once you use these identities right here. Cos squared theta is 1/2 plus 1/2 cos 2 theta. That makes integrating cos squared theta relatively easy. Sine cubed theta is 1 minus cos squared theta times sine theta. Why did I get that? Because that's the same as sine squared theta. And then do a substitution to integrate that. Let u or w, whichever you prefer, equal cosine of theta. And that's w, for example. Then dw would be negative sine theta d theta, so you just have a negative sign to deal with to compensate there. That's definitely an integral that's doable within, overall this double integral should be doable within 7 or 8 minutes. Okay? I should be able to do that completely within 7 or 8 minutes, whereas the other one would have taken maybe 40 or 50 minutes. All right, can I clarify anything there? Again, I know I have a lot of writing here, a lot of different code. I would encourage you very strongly to look at this after class. I'll put it up on the Google. Experiment with it. This code, again, just calculates, it's just a way of calculating the Jacobian matrix and the Jacobian determinant. Don't worry about the details of how it works. You do see the capital D's here, which take derivatives. And you do see a DET here, which takes a determinant. But don't worry about the slash and dot stuff there. Essentially, it's just a way of taking the derivative and then plugging in a point at the end. You can imagine this visually as well. This is the animation I showed you before. Actually, I made it even fancier here for today. We can see how different regions in an r theta plane get transformed to various regions in an xy plane. And by moving these other sliders, you can change where your rectangle is, and you can change how big it is. You can see where it gets mapped. Okay? Effectively, again, the absolute value of the Jacobian determinant is like a dilation factor. When it's bigger than 1, it magnifies areas, it makes it bigger. When it's smaller than 1, it shrinks areas. Makes them smaller. And depending on where you are, in this case, how big r is to start with, that tells you how much something gets bigger or smaller under the mapping. Here I can even show you when r is relatively large to start off with, then the area actually increases under the mapping. On the other hand, if r is relatively small to start off with, then the area decreases under the mapping. That's essentially what's going on. All right, so no questions about that. I've got 20 minutes now to talk about triple integrals, whereas in the last class I got bogged down and I only had 5 minutes. I guess I'm going to encourage them to watch the last 20 minutes of today's class with you guys. Triple integrals, in rectangular, cylindrical, and spherical coordinates. One thing to realize is there's a volume element instead of an area element. But what's the intuition behind this? You've got some solid region in three-dimensional space. I am going to keep any problems that you'd have related to this on the final exam relatively simple, meaning the solids will be relatively simple to describe, for example, in spherical coordinates like spheres. Spheres are simple to describe in spherical coordinates. So I'm going to attempt to draw a sphere centered at the origin in three-dimensional space. I can initially start by drawing a circle, and then get some perspective in here by drawing another circle, maybe about like that. Try to imagine this is a sphere. Let's call the radius capital R. This sphere is easy to describe in spherical coordinates. Rho now is not the density, it's the distance to the origin, it's the spherical coordinate rho. Rho goes between 0 and capital R. Theta is still the same theta as always. For this class, remember in physics they switch it out, the theta and the phi. But for us, theta is the angle that starts off pointing, it's the angle that you make with the positive x-axis. So it's the angle that you measure swinging this way. And usually, to get the entire sphere, you think of theta going around the horn from 0 to 2 pi. Once you've done that, it's sufficient for phi, which is the angle coming down from the positive z-axis, to not go from 0 to 2 pi, but instead from 0 to pi. This set of inequalities describes this sphere using spherical coordinates. What were the spherical coordinate conversion equations? X was rho cos theta sine phi. Y is rho sine theta sine phi. And Z is rho cos phi. Those are the conversion equations. In this section, we can now think of these as defining a mapping. You can call it capital G if you like. Capital G of rho theta and phi will be a function, a mapping, that takes three-dimensional inputs and gives you three-dimensional outputs, the coordinates of which are given by these equations. Rho cos theta sine phi, rho sine theta sine phi, and rho cos phi. It's easy to forget those. I often forget them. Okay, I've looked them up beforehand here. These are what they are. That's a mapping, a three-dimensional mapping. And just like in the two-dimensional case, you can calculate a Jacobian matrix and calculate the determinant of that Jacobian matrix. That's what this code does. And then use that Jacobian matrix, the determinant of the Jacobian matrix, in absolute value to help you do integrals in spherical coordinates. So the G1, G2, and G3 here just stand for those coordinate functions, the different conversions. Rho, theta, and phi are the new variables, the u, v, and w, so to speak. What is the Jacobian determinant of that matrix? It is, oops, gotta simplify it. It simplifies to negative rho squared sine phi. We take the absolute value of that, and we are assuming phi goes between 0 and pi, so that sine of phi is positive, or not negative at least. And we ultimately get rid of that absolute, that negative sign. This thing is the so-called volume element in the spherical coordinates. But what is a volume element? Again, we take an intuitive approach. We imagine this as being a solid. We'd like to calculate the mass of the solid without weighing it. Okay? It's a theoretical mass. Here we're imagining somehow that even though we don't know the mass of this, we know the density function. Well, I better not use rho. F of x, y, z. Actually, the book still does use rho for these sometimes. So you got to keep track of the distinction between the density function rho and the spherical coordinate rho, the different things. I'll call it f. That's going to be some function of 3 variables, and in typical units, it's going to be in grams per cubic centimeter now, because now we are talking about a real solid in 3-dimensional space. If that were a constant function, we could just take that function and multiply times the volume of the solid to find its mass, the volume in cubic centimeters to find the mass in grams. But, as usual, we are pretending it's not constant, but we imagine a little infinitesimally small chunk here. I guess I'm kind of drawing it like a cube, but if you're thinking about spherical coordinates, you actually wouldn't draw it like a cube. I'm trying to draw a little tiny cube here as my volume element, my dV, over such a little tiny infinitesimally small cube. We basically imagine that the value of the density is constant, and we imagine that the mass that would be calculated from that would be calculated from a product. F of x, y, z times dV would give us the infinitesimally small mass of that infinitesimally small chunk of this solid. And then the total mass is found by adding up the infinitesimally small masses, where you imagine integration is adding up. Up here, the total mass, m, is found by adding up the little masses. Now it's in 3 dimensions, so we use a triple integral symbol, 3 integral signs. The book typically doesn't call these solids D. They typically call it W, and I guess I'll stay consistent with the book. Integrate the dm's, add up the little dm's over W to give you the total mass, which means adding up, so to speak, these products, f of x, y, z, dV. Again, this is just conceptual, intuitive conceptual derivations, not rigorous. It's meant to give you intuition behind what's going on here. Where do these formulas come from? How do you calculate the integral? You can use rectangular, cylindrical, or spherical coordinates. Because this is a sphere, it's probably going to be best to use spherical coordinates. And in either case, in any of those 3 possible ways of doing it, you need to do it as an iterated integral, just like the double integrals. There's going to be an innermost integral, a middle integral, and an outer one. How would it typically look in spherical coordinates, for example? Well, how would it look in this example for spherical coordinates? The limits of integration would be simple. They'd just be numbers, because you can describe those limits with particular numbers. R is a fixed constant. For spherical coordinates, you calculate the integral, again, as an iterated integral. So I'm going to use parentheses here. Though when you do it by hand, you don't have to put parentheses there. This is a conceptual thing to emphasize that. You need to, well, give yourself more space here. I should have given myself more space. You're going to need to plug in these expressions in place of x, y, and z into the function. You're trying to get everything in terms of rho, theta, and phi. and then replace dv with this thing. Which sounds like it would be a very difficult thing, right? This is pretty complicated looking. F of rho cos theta sine phi, comma rho sine theta sine phi, comma rho cos phi. Don't forget, times rho squared sine phi. Didn't give myself quite enough room. D rho, d phi, d theta. Rho is going to go from 0 to capital R in this case. Phi will go from 0 to pi. And theta will go from 0 to 2 pi. So that's the thing you would do to find the mass if you know the density function f. It looks like it's going to be pretty nasty. And theoretically it could be. However, oftentimes this does simplify pretty nicely because of trig identities, like the fact that cos squared of an angle plus sine squared of that same angle is 1. Let's try an example here. Well, certainly if I did x squared plus y squared plus z squared, that would turn out pretty simple, I bet. Let's go ahead and try it here. X squared plus y squared plus z squared. That's going to equal rho squared, which you can confirm by doing this. Simplify f of, well, can I copy and paste anywhere? I guess so here. That, comma this, change the cosine to a sine. Theta to a phi, and get rid of that sign on the last one. That simplifies to rho squared. But you can't forget about this right there. That needs to be in there to get the right answer. So how nasty is the inner integral going to be? Still not too bad. We're going to have rho to the 4th times sine phi d phi. I'm just writing the inner integral here. D rho, excuse me. That's definitely doable by hand. You get a rho to the 5th over 5 times sine phi. Rho going from 0 to capital R, you'll get r to the 5th over 5 times sine phi. That's the inner integral. Now what about the middle one? 0 to pi. This thing with respect to phi. By the way, this is the typical order that most people do these things in, d rho, d phi, d theta, but once again, you can switch that around too. Do these in any order. That's the most typical order. How about that integral by hand? That's not too hard. Integrate sine, you're going to get negative cosine. Cosine of pi is -1, cosine of 0 is +1. Definitely doable by hand. Should get that. Finally, how about the outer integral? Theta goes from 0 to 2 pi. This is a constant function of theta. Definitely easy to integrate. The answer is going to be that constant, 2r to the 5th over 5 times 2 pi. So the answer is going to be 4 pi r to the 5th over 5. Okay, and you can do it all at once. Let's do the triple integral all at once. 0 to 2 pi. Tab over to here, hit the integral button again. 0 to pi. Tab over, hit the integral button again. 0 to capital R. The function is rho to the 4th times sine phi. When you don't forget about doing that. capitalize something? Rho d phi d theta, same answer. And what does that represent? This is the density, this is the mass, excuse me, of a sphere of radius capital R, whose density is x squared plus y squared plus z squared, which is going to be rho squared, which is it's the square of the distance to the origin there. The density at any given point, pretend this is inside the sphere, the density at any given point is the square of the distance to the origin. In that kind of situation, what we've just shown is that the total mass is going to be this thing, 4 pi r to the 5th over 5, which you would never expect, right? You'd never guess that that's the answer. It is interesting. That's telling you that the total mass as a function of capital R is proportional to r to the 5th, which you would never expect. So as the sphere kept increasing in radius, and the density still varied in the same way as the square of the distance to the origin, then the total mass would increase like r to the 5th does. Is there a way we could have somehow guessed approximately what this would be? Maybe based on a contour map? Well, yeah, what if we took r to equal 1 and we did this kind of thing? Let's see. Did a contour plot 3D. X squared plus y squared plus z squared is the function. I'm going to take capital R to equal 1. And let's combine this with, let's do a region function thing. Region function, arrow function. We're going to keep it inside the sphere of radius 1. Let's make it radius 2. More interesting. And actually, there's a mistake here. I need to say what z varies between as well. So this is a sphere of radius 2. Add in more contours. I think the default is 5. Try 10. And let's also do a graphics 3D. Let's make a sphere. Opacity 5 sphere. I think the syntax is to put the origin first, or the center of the sphere, and then its radius. That might work. There it is. It's not quite as nice as the two-dimensional situation, because we can't see the values of the function along these level surfaces. These level surfaces are all spheres that are all inside of each other, that are all centered at the origin. We can't see the value of the function along the level surfaces by moving the cursor. That's the downside here. Although we can, give me a minute here, we can estimate the value of this function, for example, at the point, well, at the point 1, 1, 1 is going to be a value of 3. 1 squared plus 1 squared plus 1 squared. Is that the average density? I'm sure it's not. What if it were? What if 3 grams per cubic centimeter were the average density? I then have to find the mass by doing 3 times the volume of the sphere, which is 4/3 pi r cubed, type an I, times 2 cubed. 4/3 pi 2 cubed, that's the volume of the sphere. 3 is my initial guess for the average density. 32 pi would then be my initial estimate for the mass. That's about 100.5. How close is that to this when r is 2? Probably not real close. Let's just see. Okay. Within an order of magnitude, I guess you say. Closeness. There was a wild guess with the 3. The average density is going to be more like 2.5 or something. Okay, so your problems, your completion problems for Wednesday are just about triple integrals and also using cylindrical and spherical coordinates. They're not about general changes of coordinates, but I would recommend reading that again. That's it for today.